And so please welcome the second talk of the session. It's given by Mr. Riad from Ottawa in Canada, and it's done in collaboration with the Concordia University of Montreal. So the floor is yours. The title is Flame-Made Quantum Dots.
Well, hello, and first, thank you very much to the organizers for going above and beyond and allowing me to participate virtually from across the ocean. My name is Keroles Riad. I'm a postdoctoral fellow with the Energy and Particle Technology Laboratory at Carleton University. Here in Canada, I was working with Professor Reza Kholghy, who's right there with you. And today I would like to talk to you about flame-made quantum dots. And first, I would like to start with a little bit of the story about how this research came about. And it really begins with my fascination for the technology of 3D printing and particularly the stereolithography process, which uses liquid epoxy with photoinitiators mixed within. And those photoinitiators, when they're exposed to light with a specific energy, they get excited and they trigger a photocuring reaction where the epoxy goes from liquid to solid. Now, the challenge is that all initiators currently available have some sensitivity to the UVA region of light, which exists both in the 3D printing laser and also in the sunlight, which is why you put sunscreen at the beach. And what that means is that when you 3D print a part with stereolithography and leave it outside for a couple of weeks, the initiators that are still inside the 3D printed part absorb UV from sunlight and get excited and continue to polymerize the material. And what that means is that the 3D printed part has a continuously changing properties. And at some point, those material becomes so brittle and so that it fractures and breaks apart within a couple of weeks. So it's not very stable, it's not very useful. And so my goal is to create new catalysts that are sensitive exclusively to light outside of the solar spectrum, which is essentially anything lower than 300 nanometer, which is completely blocked by the ozone layer. And that way I can have catalysts that is sensitive to UVC light, not UVA light, so that I can 3D print with the UV laser, but it will be not sensitive to sunlight. And I would like to do that with quantum dots. And quantum dots are a special kind of semiconducting nanoparticles whose band gap energy is a function of their size once the crystal size is below a certain threshold called the Bohr diameter. So in this graph here is quantum selenide, where the crystal size goes from 150 angstrom all the way down to 17 angstrom. And you see as the crystal size decreases, the absorption wavelengths plotted on the x-axis shifts to the left to lower values, and that means a higher bandgap energy. And so in essence, as the crystal size decreases in quantum dots, the bandgap energy increases. And so the first step for my research was actually demonstrate that semiconducting nanoparticles can actually do the chemistry, can do the photocuring, because up to that point, it has not been shown. And so early in my PhDs, this is what I did. And in this graph here, it shows the epoxy consumption, which is a measure of the reaction, photocuring reaction kinetics as a function of light exposure time. And in blue, when you don't have initiators, you don't see any reaction. But when you add B25, which is a mixture of anatase and rutile crystal structures, titanium crystal structures, and it is a gold standard for catalytic activity, you see a typical photocuring pattern. Now, the problem here is that B25 and titania's bandgap energy is within the UV region. So that region is still unstable under sunlight. And so the next step is to make the quantum dots with the right bandgap energy, which is above 4.1 electron volt or lower than 300 nanometer wavelengths, which is what brings me to this work. Now, quantum dots last year had a market of $4 billion, and that market is forecasted to grow to $8.6 billion by 2026. And that's because you have a lot of different applications. Some of them are listed here, goes from photocatalysis to UV protection, gas sensing, high temperature superconductors. But they're challenged with two main obstacles. Number one is scalable synthesis, and this is obviously very common in nanotechnology, where the nanoparticles are typically made with chemistry, and which is expensive, complicated, and very difficult to make the nanoparticles at a scale large enough for the commercial applications to be widely available at an affordable cost. The second challenge is that their pure quantum dots are unstable mechanically, chemically, and thermally. And one example of that is that if you have a catalytic or a gas sensing application where those particles need to operate under elevated temperatures, those high temperatures would lead the crystal particle, the crystal size to grow. And because the quantized effect is a function of crystal size, that could mean that the crystals would grow beyond the Bohr diameter, and that would eliminate the quantized properties. So this is an example of thermal instability. So the question that I had at this point is, can FSP make quantum dots with the right band gap energy for my application? And before this, there was only one paper that has made quantum dots with FSP, and that's Professor Madler's work making zinc oxide quantum dots. And as you see in this graph here, he made particles or zinc oxide particles of 12 nanometer, 4 nanometer, and 3 nanometer in crystal size. And as you see, as the crystal size decreases, my slide doesn't want to move. The wavelengths shifts to low has a blue shift, so to lower values, and that means higher band gap energy. And the way Professor Madler's pushes that crystal size to the extremely small sizes you see here is by adding silica. And he reported the silica loading using a factor X, which essentially represents the percentage of the metal oxide. So X equal 1 is 100% zinc oxide, X equal 0.9 is 90% zinc oxide, and so on. And so as you see here, as the X decreases or the silica loading increases, the crystal size decreases. And as you see in the plot, that means that wavelengths decreases and band gap energy increases. Now, as you see here, even with the 3 nanometer crystal size, the wavelengths is still much higher than the absorption wavelengths is still much higher than the 300 nanometers that I would like to get lower than. So I decided to try to push this further, and in here I show talk plots, which is the conventional way of reporting band gap energy. And in this case, I again still with zinc oxide, and I push X all the way down to 0.1, which means that it's 10% zinc oxide, 90% silica. And you see the quantized effect here very clearly. So the band gap energy plotted on the x-axis increases as the X decreases. So the silica loading increasing here. And you clearly see here with X equal 0.1, you have the zinc oxide quantum dots band gap energy to be well above the 4.1 electron volt threshold that I would like to exceed for my application. I also tried to generalize this approach with other materials. So I also made quantum dots with titanium and tin oxide, and it's fairly consistent where you see as X decreases, you have a clear quantized effect where the band gap energy increases to higher values here in both cases. Now, if you read quantum dot literature, you always have those beautiful, colorful pictures because within the visible spectrum, the quantized effect translates to a color change. So the big particles or the bigger crystals have a red, are within the red region of the visible spectrum. And then as the particle size or the crystal size decreases and the band gap energy increases, that means that that translates to a color change into green and blue for the smaller size, for the small crystal size. Now, as you see in all of my particles, the band gap energy is always in the UV region of light. So they're all white to my eye. So they're visually boring. And so I got jealous and decided to make copper oxide quantum dots because at bulk size, copper oxide is actually in the dark red region of light. And so the quantized effect means that it would, the increase in band gap energy would actually translate also to a color change, which is actually exactly what you see here. So the bulk copper oxide is dark red, and as you add silicon, the crystal size decreases, you have the increase in band gap energy, which translates to change of color into green, blue, all the way to white once that band gap energy goes into the UV region of light. So essentially, we're able, just by selecting the right semiconducting material and the silica loading, we're able to make quantum dots with any band gap energy between the UVC region all the way to the dark red part of the side of the visible spectrum using the FSP scalable synthesis process. Now, going back to the literature, with quantum dots, with wet chemistry quantum dots, you have those beautiful TM pictures of single crystals that are very well defined and very easy to measure the crystal size here. Now, my quantum dots might look like this, and it's still relatively easy to see the crystals here, but as typical with all flame-made particles, they're very agglomerated, which tends to beg the question: is are FSP quantum dots as good as the ones made with wet chemistry? And the answer here is that it depends. And in many cases, the silica embedded flame-made quantum dots are actually better, and that's what I would like to talk about next. So we talked about this, the scalability challenge of quantum dots, and I think with being able to make them with FSP addresses that to a large extent. Now, the other challenge I mentioned is the stability, and in here we should talk about the role of the silica matrix when it comes to stabilizing those quantum dots. And it's in the literature, there's a lot of information supporting the idea that embedding the quantum dots in amorphous matrices like silica actually enhances the stability of quantum dots while also preserving their unique properties. And so we had a project last summer where an undergraduate student actually tried to verify the literature for the FSP made quantum dots. And essentially, he made zinc oxide particles, and in here it's preliminary data, it's incomplete, so there's a lot of work left to do. But essentially, here with XRD, we're only able to measure crystal size for the pure zinc oxide, because once you have the crystal size being very small, and with the amorphous silica, it actually becomes impossible to measure crystal size with XRD. But as you anneal those particles at 300 degrees C for 1 hour or 3 hours, you see for the pure zinc oxide, the size increases from 8.2 to 13 nanometers, which is a 60% increase in size. With X equal 0.7, so 30% silica, you start being able to measure the crystal size because there's a little bit of growth. However, that 6.9 nanometer we're able to observe after annealing at 300 degrees for 3 hours is actually the same as the crystal size I was able to measure with UV-Vis, with solid-state UV-Vis for unannealed particles with 30% silica, which was at 6.9 nanometer. And there's an important distinction here to make of what size is actually measured with XRD and UV-Vis. With XRD, you measure the average crystal size. With UV-Vis, because you measure onset absorption, you actually measures the largest crystal size. So there's a bit of a shift in the size distribution because of annealing, but it's not as significant as with pure zinc oxide. Now, with X.3 and X.1, there's no growth sufficient enough to be able to detect the crystal size with XRD. So there's still a lot more work to do here to actually have a complete picture. But so far, the data we have does not contradict the literature that the silica actually stabilizes the quantum dots. Now, with catalytic activity, you also have to think a lot about morphology, especially when you have an amorphous matrix. And I go back here to the work with Professor Taliki, who compared a core shell structure where the amorphous matrix would hermetically seal the surface, which would actually kill catalytic activity, compared to mixed phase particles where you have the segregated particles with distinct amorphous and crystalline domain, which actually have a high catalytic activity. And so I think the proof in the pudding here was catalysis. So in here, I compare the performance of pure titania as well as with 20% and 30% silica, so it's X equal 0.8 and 0.7, and as well as X equal 0.1 here. And you see, even with 20 and 30% silica, the kinetics for the catalysis here is higher than P25, which, as I mentioned earlier, is the gold standard for photocatalytic activity. So clearly, the amorphous silica does not hermetically seal the surface, so the catalysis is still possible. Now, you will be able to observe here that as the silica loading increases, the reaction kinetic decreases. And when you have x equal 0.1, there's actually essentially no reaction. And this actually goes to the advantages of quantum dots and goes back to why this research started in the first place, which is to have the catalytic reaction taking place with UVC light, but not UVA light. And this is exactly what you see here, where essentially with titanium quantum dots with UVA light, you don't see any reaction the same way as you had in the previous graph. Without any initiator under UVC light, you don't see any reaction. But with UVC light, you have the typical photocuron reaction again. So what this is essentially is achieving the goal of the premise of the research, where you want to have the quantum dots to control what kind of light actually triggers the catalytic application, the catalytic reaction. Next for me is to assess the mechanical stability of the photocured resin, which usually is the ultimate goal here. So in conclusion, we're able to synthesize silica embedded quantum dots with any band gap energy between the UVC and dark region of light using the scalable FSP technology. And preliminary data agree with the literature that the silica matrix enhances the thermal stability of the FSP made quantum dots. And that silica matrix does not hermetically seal the catalytic surface, allowing the reaction to take place. And that FSP made quantum dots do allow control of what kind of light actually trigger catalytic applications, catalytic reaction. And I use the example of the epoxy photocuring with the goal of enabling stable 3D printing resin. There's a lot of people to thank here. I want to thank everybody at Particle Technology Laboratory, especially Professor Batsinis and Dr. Carsten Wagner for their support and hospitality, and Frank for the TM pictures, as well as everybody at the Concordia Center for Composites with Professor Hoa and Heng Wang there. And it's time for questions. Thank you very much for listening, and I'm eager for the discussion.
Yes, thank you for this interesting talk, Mr. Riad. So the floor is open for questions.
Thank you for the nice presentation. Regarding this copper oxide, right? How do you? So you may have copper +1, copper +2, copper +1 is red, copper +2 is black.
Yes.
How do you really know that it's not so an oxidation state effect, and this is a purely size effect? Did you measure XPS?
Yes.
Like
so it's, yeah, we did do XPS to confirm that. And in the paper, we compare the different oxidation state with copper oxide, where we're able to demonstrate that the XPS, based on the XPS data, what we have is copper oxide, the CuO oxidation state. I hope this answers your questions.
Hi, Kiro. George
Hello.
Here. Nice to see your presentation. It was not clear to me. You coated the particles, right? I guess using a torus ring, or how did you introduce the silica coating?
I didn't coat it. So the precursor mixture had both the titanium and the silica precursors. And so it's a mixed phase. So part of Tilika's work, where is it? Part of Tilika's work where she compared the core shell structure to the mixed phase structure was that the core shell was made using a ring on top of the flame, where the silica is added after the core material is built. So this is how the core shell structure is made. With mixed phases, when the precursors are mixed inside at the same time in this range, so that you have the mixed phase. And so you have the sort of the metal oxide is within the matrix without being coated. And this is really important because the surface has to still be available for catalytic reaction. With this catalysis or gas sensing, the surface still needs to be available. And so you cannot hermetically seal it. That's really critical.
Maybe I missed it. Did you show microscope images of your particles of different contents of silica to see how they look like?
Yeah, so this is
with silica. These, I thought these were the pure quantum dots, or not?
No, so this is X equal 0.7. So this is 30% silica.
Okay.
And you see both the crystalline fraction, and you also see the amorphous silica.
I see.
Does this answer your
Good.
question?
Thank you.
So any more questions? So that's not the case. So let's thank the speaker again. Thank you very much.
Thank you so much.